Imagine you're building an application. On startup, you connect to a database, parse configuration files, warm up a cache, and spin up a reporting engine. The problem, your users might never open a report, yet you've made them wait for it every single time. This is the core tension that lazy initialization solves. Instead of paying the cost of creating something when your program starts, you defer that work until the moment it's actually needed. Today, we're going to trace exactly how that works, the pattern, the implementation, the pitfalls, and when to reach for it. Let's go. Why would you ever build something you might not use? The answer usually is habit. Eager initialization, creating everything at startup, is the default mode for most developers. It feels safe. It feels clean, but it comes at a price. Every heavyweight object you construct at startup adds to your application's cold start time and memory footprint, even if that object is never touched in that particular session. The alternative is lazy initialization. Defer the construction of an object until the first time it is actually requested. After that first access, the initialized value is cached and returned directly on every subsequent call. The object is created exactly once, just not necessarily at program start. The formal definition is simple. An object's initialization is deferred until the first time it is needed. Three properties follow from this. First, it is deferred. The object is not created when its container is constructed, only when its value is first accessed. Second, it is transparent. Callers interact with a lazy property exactly like a regular one. Third, it is idempotent. The expensive initialization runs exactly once. Every subsequent access gets the cached result. The pseudocode is 3 lines. If the value is none, call the factory and store the result, then return the value. That is the entire pattern. The clearest way to see lazy init is to compare it against eager init on a timeline. In an eager system, the app starts and immediately the database pool is created, the config is parsed, the cache is warmed, and the report engine is spun up. By the time the first user interaction is possible, all of that work is already done, paid up front. In a lazy system, the app starts and nothing is created. The first time the user actually runs a report, the report engine initializes. The first time a query is issued, the connection pool is created. The cost moves from startup to first use. For code paths that are always hit, there is no net gain. But for rarely used features, lazy init can dramatically reduce both startup time and memory consumption. Python implementation using a descriptor makes the pattern reusable. Define a lazy property class. In its constructor, accept a factory callable, the function that will create the value, and set the cached value to none. In its get method, check if the value is none. If so, call the factory and store the result. Then return the stored value. To use it, declare a class attribute as a lazy property, passing the factory. From that point on, accessing the attribute reads exactly like a regular property. The descriptor handles all the plumbing. Python's standard library ships a ready-made version of this as functools cached property, which covers most everyday use cases without writing a descriptor yourself. Lazy initialization has a well-known adversary, concurrent access. If two threads both check the value at the same instant and both see none, both will call the factory. This is a race condition. The fix is double-checked locking. Check if the value is none outside the lock. This is the fast path for the common case where it's already initialized. If it is none, acquire a lock. Inside the lock, check again, another thread may have beaten you to it. Only if the value is still none do you call the factory. This eliminates the lock cost on the hot path while still protecting the initialization code. Lazy initialization shines in specific contexts. Database connection pools are the textbook example. The pool should open only when the first query fires, not when the application boots. Configuration parsing is another. Only parse the sections you actually read. Report engines, plugin systems, and ORM relations all follow the same logic. Load on demand, not on startup. Django's ORM has used this pattern for related object loading since its earliest version. Accessing a post's related comments doesn't hit the database until you actually iterate over them. The pattern is universal enough that most modern languages or frameworks provide a first-class version of it. Lazy initialization is not free. The benefits are real: faster startup, lower memory for unused features, and automatic caching of expensive results. But the costs deserve equal attention. First access latency is the most obvious. The cost doesn't disappear, it moves. Debugging becomes harder because errors surface later and further from their origin. Testing is more complex because initialization side effects are hidden until the property is accessed. And thread safety demands careful attention. The rule of thumb is pragmatic. Use lazy init for resources that are both expensive to create and not guaranteed to be needed. Lazy initialization exists in every major language, under different syntax but the same principle. Python provides functools cached property as a built-in decorator. Kotlin has the byLazy delegate, which is thread-safe by default. Java uses a volatile field with double-checked locking. JavaScript can use the nullish coalescing assignment operator. In all cases, the surface reads like a plain attribute or property. The laziness is entirely behind the interface. Pick up any large code base in any of these languages and you will find this pattern because the problem it solves is not language specific. Thanks for watching.